I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism Podcast, an exploration of the past, present, and future of material science and engineering. I'm Taylor Sparks, an associate professor of material science and engineering department at the University of Utah, and I'm joined by my co-host, Andrew Falkowski. Andrew, how you been, man?
I've been doing pretty well. Getting to the end of my program down here at Texas A&M, and it's actually gotten hotter. I think a couple episodes ago I said it was pretty hot down here, but the temperature just keeps climbing every single week, and so it's made trudging to the lab and to the gym quite unbearable, but it's good.
Texas doing Texas things.
Yeah. The weather here is very sporadic. Like 1 second it'll be like hot, sunny, and then the next it'll just be pouring rain. It's pretty wild.
Crazy.
But the program itself has been really good. I've learned a ton. If you're an undergraduate who's at all interested in potentially going to graduate school or wanting to find out what it's like, the REU program is definitely the way to go.
For sure. Well, we have a month left before school, and I've got big news on my end. Our department just merged with the metallurgy department. So we actually, to my knowledge, were like the last department in the nation that had a separate metallurgy and material science department. But we've just merged, which makes us, it's brought in a ton of new people. Really is going to allow us to synergize and teach better. So I'm jazzed about that. And I just got tenure. So I am now an associate professor. So great things happening on this end.
Congratulations on that. And that's really exciting about the merger. I'm interested to see what new opportunities and resources come up as a result.
Yeah, there's going to be a ton of new opportunities. Well, okay. So today we're going to be talking about something that, this is how I start every year when I teach my Introduction to Material Science course. This is exactly what I start with. I start listing the different types of materials because these are mostly general engineering students, not necessarily material science and engineering students. And we start talking about the general types of materials. You've got your metals, your ceramics, polymers. We introduce the idea of electronic materials and composites. And for all these things, the students can picture something in their mind. And so by the end of that introduction, they sort of have a feel like, okay, that's the sort of things that we're working on. And that's the point where every year I love to pose this question and bring out my demos, which are a bunch of little chocolate Lego men that I've cast into like little Lego molds. And I ask them, what else are materials? And I say, is chocolate an engineering material? And this leads to a discussion about what does it mean to be an engineering material? And I suggest that means simply that it's something that can be engineered or designed in order to better fit its properties for some given application. So let me ask you this, Andrew. Does chocolate fit that description?
Absolutely. As we'll discover in today's episode, there's a lot of material science concepts that go into making good chocolate. It's a really good example as well because it's a very ubiquitous material that everyone has experienced and is familiar with.
Absolutely. And there's so much money involved with it. This is billions and billions of dollar industry, I'm sure. So of course people are going to engineer it and try to do better so that they can sell more of their products, right? Chocolate can be tuned not only in terms of composition, like you've probably heard of milk chocolate, dark chocolate, white chocolate, right? But you can also change all sorts of other properties. You could have porous chocolate sponge cake. You can have the melt in your mouth chocolate truffles, maybe the clay-like chocolate fondant, chocolate bars with that nice snap as you break a piece off. There is so much you can tune, and that requires a lot of engineering, and that's what we're going to get into in today's episode. So maybe to start with, Andrew, can you tell us what is chocolate? What is it made up of before we start trying to change it and mess with it? What's it actually made up of?
Right, so I guess with the modern chocolate that we're familiar with, there's essentially four main components. The first is going to be called cocoa butter. The second is going to be, they call cocoa solids, and these are essentially just particles containing all sorts of very flavorful molecules that come from the cocoa bean. Cocoa butter also comes from the cocoa bean as well. These are fatty triglycerides. And then you're going to have sugar and milk. But the first thing we want to talk about is the cocoa butter, because that leads us into talking about different crystal phases. So one thing is that fats exhibit a phenomenon known as polymorphism.
Now, is it just fats that do this, or do all things have polymorphism?
Everything that can form a crystal structure or can take different forms will exhibit this. And so cocoa butter specifically exhibits this polymorphism. And what this means is that it can transform into different, we call them phases, which are different arrangements of the molecules within it. And they'll orient themselves from less stable, lower melting point formations to higher melting point formations. And they do this as a result of thermodynamics, as we'll get into. And so these different formations result from different arrangements, like I said, and packing of the different fatty chains or strands of chains of carbons and that come off of these different molecules. And so one way to sort of think about this is, imagine you're packing the back of a car. You have a bunch of stuff you want to put into it. There's a lot of different ways that you can pack the stuff in and arrange it in the car. Some are going to lead it to topple over while you're driving, while some will be much closer, denser packed, and the stuff's going to stay where it is even as you make turns. And so that's what we're talking about, where we have different arrangements.
Okay, and I can imagine with molecules, if you are able to, say, pack them closer together or further apart, we know that is going to change properties. Everything from melting point to how stiff it is, all sorts of properties get adjusted as you change, their arrangement.
Mm-hmm. Yeah, absolutely. And that's where we sort of start to get into the different properties of chocolate that can result. And so the fats that are in cocoa butter are called triglycerides. And these have a tuning fork shape, if you've ever seen that, where you have essentially two parallel strands that form together into one. And then these can actually become very complicated. So you'll get different lengths at different parts of the tuning fork shape. And what's really interesting about these is that the different types of triglycerides that you'll see in chocolate depend on the geographical region in which the cocoa bean is grown, which I think is really cool. And so a lot of environmental factors go into determining what kinds of fats you'll see in your chocolate.
In studying for this episode, I saw that, and it was really surprising. I guess I'm not surprised. It should make sense, because when you eat chocolate in different places, it kind of does have its own regional flavor. And I always assumed that was just due to the things that they maybe added or didn't add to it. But it might actually, it's not might, it is in fact related directly to how the cocos just create these fats differently in different areas.
Yeah, right. And so within a given piece of chocolate, you'll see anywhere from 50 to 60 different types of triglycerides present. And so as a result, when these organize, they actually organize by size. So triglycerides of a certain size will generally form a crystal structure and pack together with other longer triglycerides, and the same with the smaller ones. And so within cocoa butter, they have found over the years, there's been actually quite a bit of debate within the literature, but the current number is 6 different crystal forms that are distinct that form within cocoa butter. And these are aptly titled 1, 2, 3, 4, 5, and 6.
And sometimes they call it beta. If you hear about the beta phase, that's the 5 and 6, beta and beta prime.
Mm-hmm. And so structure 1 and 2 are mechanically soft and very unstable. Over time, these will transform into denser types of 3 and 4 if they're given the chance. This essentially just stems from them, like the molecules wanting to get closer together and form a more stable packing order. And so 3 and 4 are also very unstable. These are soft and crumbly. They don't have that brittle snap that people are used to with a chocolate bar when you try to break them. And so if you buy chocolate and you melt it down and let it harden, these are the crystals that will form. This chocolate's really soft to the touch. It has a matte finish and it melts super easily.
Yeah, I remember the first time I saw this, I think I left like a Hershey's Kisses or something in my car in like the little dashboard area. And I saw it afterwards, and when I opened it up, dude, I thought that it was moldy. Like I was looking at it thinking like, what happened to this? Like it had kind of that matte color, but had like white spots on it. So what's happening there, Andrew?
Right. So going with the trend of transforming into a more and more stable form, essentially what happened here is that chocolate eventually transforms from that 3 and 4 structure into a type 5 structure, which is one of the most stable and is the structure that's present in the chocolate that we know. But in order to do so, right, the triglycerides and the molecules are trying to get packing closer together. But when they do that, the things that were previously contained within the sort of network of molecules, right? When they're getting packed closer together, there's going to be less space in there. So what happens is the sugar and other fats that are within the chocolate actually get ejected out of the crystal structure and will appear on the surface of the chocolate. And this is called bloom.
Yeah, and so when I teach my material science class on the first day of class, I've got some chocolates that I've taken care. We've done a process that we're going to describe later to prevent this from happening, and I have others that I just melted and poured them right into the mold. And if you wait a couple days, the Lego men that I have taken care to do something called tempering on, they look beautiful. They have that nice glossy finish. When you eat them, they taste just like chocolate from the store. But the other Lego men, the ones that I just cast right into the mold, they look like they have leprosy. They're like zombie Lego men. They look terrifying. And I tell the students, these are the exact same thing. All I did was I did an extra little magic, thing called tempering on this one, and this one I cast right into it, and they can never believe it because the bloomed chocolate, it's kind of mealy and soft and crumbly as opposed to that nice snap. So once you chew on it, it tastes kind of the same, but man, texture is such a big part of how we perceive flavor in food that you'd never guess they were the same thing.
Mm-hmm. And that texture and the sort of taste and the experience of eating chocolate is almost just as much a part of the flavor itself. There's a perspective of looking at materials and of the physical world called psychophysics. And essentially, the idea behind this is that we have different expectations of how things are supposed to smell, taste, feel, sound, and these sensations are tied to that object and become a part of the experience when we're using it. So one example that a lot of people might be familiar with nowadays is the difference between reading on a computer or a tablet and reading a book. A lot of people really enjoy the sort of tactile feel of turning pages. There's even the smell of the book, the texture of the paper, and when you're reading it digitally, those aspects of reading a book are completely gone. And so that's why you see people still, despite having, computers and all these things, still use physical books.
Oh, absolutely. I totally agree. Like there is something about all those other senses being involved that is more enjoyable.
Mm-hmm. And the same can be said for chocolate as well. When you eat it, you want it to. It's hard when it enters your mouth and then it melts, and essentially you get this cooling effect on your tongue. All these nutty, earthy, creamy, sugary flavors. Are ejected out of the crystal onto your tongue. You start tasting all of that. When you snap it, there's this nice snapping sound, and all of that contributes to the experience of eating chocolate, and as well as it contributes to our expectations of how chocolate is supposed to sound, feel, and taste. And so when a piece of chocolate doesn't have those, it feels about as empty as reading a book on a computer.
So I joke, we have family. My dad, his first language is German. His mom immigrated from Germany. So we still have lots of family over there. And when we go and visit them, they always give us a list of things to bring over, things that they can't get in Germany. And I was blown away this last time we went and visited. He wanted like tons of giant like crunch bars, like Nestle crunch bars. And I was just like, you live in Munich, man. You're in like the chocolate capital of the universe and you want crunch bars? It just blew me away. Like it seemed so wrong. But in any case, having introduced kind of what chocolate's made of and introduced this intriguing concept that you can do something to chocolate to prevent it from blooming, which again is when the sugar and the fat sort of separate from the cocoa butter. We're going to dive in after a break in what it is that you can do to a chocolate to prevent this from happening that turns into big business for all these chocolate companies. We are excited to announce MatMatch as a new sponsor for our podcast. MatMatch is a company that's passionate about material science and whose goal is to help connect materials engineers with materials providers and suppliers. For example, as you design materials for some given application, maybe your calculations suggest that an ideal material would have a density of less than 3 grams per centimeter cubed, an electrical conductivity of 20 million Siemens per meter, and a yield strength of at least 300 megapascals. The next question that you might have is, all right, what magical material is this? And then where can I find it? MatMatch makes this easy. When I type these constraints into their website, I immediately see that there are 44 materials that match this criteria. And I can buy these materials from 2 different suppliers. The whole process is super quick and intuitive, which is probably why their platform is used by over 1 million engineers each year. Best of all, for our listeners, searching for that perfect material is completely free for materials engineers. Head over to matmatch.com and check out how useful it might be for your next engineering project.
And so right before the break, we talked about the experience of chocolate and how chocolatiers want to make sure that we get chocolate that has those specific properties that we're all used to meet our different expectations. So they want to create these type 5 crystals in their chocolate. But unfortunately, the type 3 and 4 crystals are the easiest ones to create. And those are the ones that are unstable. They produce the bloom, the sugar and fat that appear on the surface. So the way that we get these type 5 crystals is through a process called tempering. Taylor, do you want to talk a little bit about that?
I'm sure we'll have future episodes that also talk about these ideas, but the fundamental material science concept behind this has to do with nucleation and growth. So anytime that you start with a material in its liquid phase, if you cool it down below its the melting point, so now its freezing point as it starts to freeze, well, as you cool it lower and lower below that point where it should start to freeze, the driving force gets stronger and stronger for it to actually solidify. And that whole process of transforming from one phase to another, in this case, going from a liquid to a solid, that is dictated by 2 processes. One is called nucleation, meaning you have to nucleate a tiny little part of your material that is now, say, a solid. And then the other part of the process is called growth, meaning that little crystal that just grew has to grow, okay? So nucleation and growth, these are core material science concepts, and we'll just give you sort of the key points. First off, what's driving it to happen, right? This is always a difference in free energy, right? Everything that happens in the entire universe happens because it lowers its energy, meaning from where it started to where it ended, it went down in energy. It's never going to go uphill in terms of energy. And then this driving force, it gets bigger and bigger and bigger the further you go below the freezing temperature. So if you're only 1 degree below the temperature, you don't have a very big driving force. But if you're 10 degrees or 100 degrees below that temperature, you have a really strong driving force for that reaction to occur, for it to go from a liquid to a solid. Okay? Now, at the same time, you've got a driving force. There's something that actually prevents it. There's a retarding force that stops this reaction from occurring, and that is called surface energy. You've probably heard that term before, that surface energy. Any surface, whether that's the top of your desk and the air between it, or even within a solid, if you've got 2 regions that are just oriented in slightly different directions, along that boundary, that's a surface. All of these surfaces have energies, right? And so as you go from a liquid to a solid, you're creating an interface between that solid and the liquid. That interface is a surface that costs some energy. And you had this really interesting effect happen. So on one hand, on a per volume basis, the larger the volume that converts from liquid to solid, that saves you energy from a free energy standpoint. But that little crystal, maybe let's assume it's a sphere for a moment, all along the skin of that sphere, that's costing you energy. And if you have a really, really, really small nuclei that formed, then you don't have very much volume, but you have a lot of surface area. And so overall, that's not favorable. The additional energy that it costs the system to form that interface and surface is going to make it less likely to form. But if you can form a great big radii, now you've got a whole bunch of volume that is growing at a larger rate than the surface area is, and so it becomes favorable. And this leads to this interesting idea that there's a critical radii. There's a critical nuclei size where if you're smaller than that, the particle will actually redissolve because it's energetically favorable due to the surface area constraint. But if you're larger than that critical nuclei size, it will keep growing. So all you have to do is get these things over that hump, and once they're bigger than a certain size, then they'll just keep on growing, okay? Another way to think of this is that there's sort of like an activation energy that has to be overcome. Now, when it comes to nucleation, there's two types, and we might do a whole nother episode on this, but there is homogeneous nucleation and heterogeneous nucleation. The key difference is that in homogeneous nucleation, we're talking about, let's say, the pure liquid and a solid sort of spontaneously forms right in the center of it, but it's all the same material. So the only interface is between the liquid and the solid. In heterogeneous nucleation, it's a little bit different. That's assuming that you've got your liquid, but that liquid probably exists in a container of some sort. So what happens about the solid that chooses to form right on the surface of the container? Well, now you have different surface energies to consider. There's the surface energy between the solid and the liquid, but also between the solid and the container wall maybe. And depending on what those energies are, this typically will lower the activation energy necessary for nucleation. It makes it easier. It doesn't change the size of that critical nuclei, but it lowers the energy needed. One way to think of it is, instead of forming a little sphere on a surface, now you're forming like just the cap of a sphere, just the top part. And so that changes your volume to surface area ratio, and it's going to make it easier for these things to form. Okay? So what dictates growth? Once you've formed your little critical chocolate nuclei, what's going to dictate growth? There's a couple of things. First off, there's your attachment frequency, which is how quickly new atoms are going to come and be able to diffuse to the surface and attach. Since it's relying on diffusion, which is moving atoms as they sort of hop through this liquid, that is a temperature-dependent process. The higher the temperature, the better. But on the other hand, the lower the temperature, meaning if you're really far below that transition temperature when you'd expect the freezing to occur, then you're going to have more and more of these critical nuclei that were big enough that they didn't redissolve. And so the max rate of transformation, or your max rate of growth, is going to be kind of it'll be in between these two values. It can't happen at high temperatures because you won't have many nuclei, and it can't happen at low temperatures because your diffusion's no good. So it picks a sort of intermediate temperature, and that's when you get your maximum growth rate.
Going back to the nucleation really quick, if I'm not mistaken, it doesn't necessarily have to even be the sides of the container. It can be other particles that are within the solution as well, right?
Oh, absolutely. I mean, if you ever seen like a cold water bottle that maybe was in your car in the winter, and then you picked it up and all of a sudden it freezes before your very eyes. Check that out on YouTube if you haven't seen this before. It's called super cooled water. That often starts right at the edge of the bottle, but you're absolutely right. You could put something in there that it could start to freeze from or solidify around in the mix. And that's exactly what we do with chocolate tempering, right? There's a couple ways to do this, but in one instance, you can actually take a little seed crystal of the chocolate in the phase that you want. Remember that Andrew said you had these 5 phases, right? You've got 1, 2, 3, 4, 5, and that beta phase is the one that we're interested in. That's the type 5 crystal structure. So if you take little tiny crystal structures of that and you sprinkle them into your chocolate as it's cooling down, instead of having to go through the whole nucleation process, which is going to be slow, it's just going to immediately start to grow on those seed crystals, and it's going to grow in the same way that it existed, which is the correct structure.
Mm-hmm. The same idea of using seed crystals to form something and lowering that activation energy is also the reason why sometimes you'll see snow falling when it's above freezing temperature for water. Because there are enough particles in the air that can lower that activation energy or the surface energy, it allows for snowflakes to form.
Yeah, and it has lots and lots of, obviously, industrial applications. If you want something to happen faster, you can seed it, right, to make heterogeneous nucleation occur as opposed to homogeneous.
Okay, so there's also another way that you can get these seed crystals to form in your chocolate. So we know that as you cool it down, a variety of different crystal structures are going to form. Some of these are going to be more stable than others, as we've discussed. So once you cool it down to a certain level and it becomes solid, you can then reheat it to a certain temperature at which the unstable forms are going to melt. However, those stable type 5 crystals are going to remain in their solid form, and then those are going to become the seed crystals for when you cool it back down again.
That's so cool. So, okay, you had it totally melted, so all the phases, they're gone. You just have liquid. You then solidify it, and now you've got a mixture probably of all 5 of these phases, but mostly the ones that you don't want. And then you're saying that you heat it up until all the phases that are undesirable are molten, but the other phases which are desirable are still just barely still solids?
Mm-hmm.
So what sort of temperature range are we talking about? That can't be a very big window.
So this is going to depend a lot on the type of chocolate. If you're doing milk chocolate versus dark chocolate, and that stems a lot from the composition of the chocolate itself in terms of the ratio of cocoa butter to the cocoa solids. But anyways, getting back to this, essentially what you're going to want to do is once you start to heat it up, you're going to want to hold it at about 31 degrees Celsius. This is when all those other unstable phases of the chocolate are going to melt down to liquid form, but you're still going to keep the solid forms of those type 5 cocoa butter crystals. And so when you're doing this, you actually want to be extremely careful, because if you go even 1 or 2 degrees more, then these type 5 seed crystals will melt back down to a molten state and you'll have to start all over again.
Yeah. In fact, it's kind of interesting from just a curiosity perspective. The type 5, which is the highest melting point phase, and it's the one that we want, it melts at like 34 degrees, and the temperature of the human body is 36 degrees. Like it almost is like we were made to eat these things. Like it's just perfect to melt in your mouth, right? And if you hold it in your hand long enough, it will melt. So let's see. Okay, so we know how to make type 5 crystals. We can either seed them, or, like you said, we can just hold it at a very careful temperature. Now, nowadays, we've got furnaces and electronic temperature control units that it should be pretty easy to just hold it at that temperature. That would certainly be more convenient than having to grow these little crystals. But in fact, it's much more desirable to do it with the crystal growth method. And that's because we haven't told you about something, and that has to do with the size of the crystals. It turns out to be very desirable to get the type 5 crystals, but to get as many really small ones as possible. Maybe you've noticed this with ice cream. Have you ever noticed with ice cream, if it's a little bit older and it's been in your freezer for a while, that it's kind of separated, that you've got like the big ice crystals as opposed to like the ice cream crystals, and it's kind of grainy, and again, the texture is just all wrong. You want small crystals to avoid that, and it's the exact same in chocolate. It's a better snap. It's a much better material if you have lots of really small type 5 crystals. And the best way to do that is to take the chocolate that Andrew just described, that you held at a certain temperature and it solidified. So these are going to be great big grains. But then you shave it. You grind it up and you shave it into a bunch of tiny little crystals. And then those are going to be at maybe room temperature. You add those to your molten chocolate. So the temperature is going to now meet in the middle, because you're adding cold shaved chocolate crystals to the molten chocolate. So that's going to bring it right near that 31 degrees, while also providing lots and lots of really small nucleation sites, so that overall you can transform the whole thing and have lots of small crystalline regions.
So now that we've talked about how to make chocolate, we're going to take a couple steps back and actually talk about how you go from the cocoa bean to the chocolate bar. Because if you go down to a jungle where they grow cocoa beans and you take one off the tree and you eat it, it's going to taste terrible. It's going to be fibrous. It's going to taste bitter. It's not going to taste anything like chocolate. And so the way they get it to the chocolate that we know is quite fascinating. So what they'll do is they pick all these cocoa beans, and cocoa beans are really interesting because they don't grow in the branches. They actually grow off the trunks of the trees themselves, which is very prehistoric kind of looking. And what they'll do is they'll just put these in a pile and leave them to rot for 2 weeks. And essentially what's happening is the cocoa beans are decomposing and fermenting. And so this has a couple like benefits and reasons why they do this. First, it kills the seeds with them, preventing germination. And then during this fermentation process, the molecules that are responsible for some of those fruity flavors of chocolate, these are called esters. These are created via a reaction between the alcohols and the acids in the cocoa bean. And these reactions are heavily influenced by the rotting time, the ripeness of the bean species, and even the weather that they're rotting in. And so these intricacies are rarely discussed when you're talking about chocolate, and that's because they're well-kept secrets by chocolatiers who spend a lot of time and research into sourcing their cocoa beans.
So that's all the trade secret. That's how it comes in then. And that's so cool, because that's the natural part of the process that happens sort of on its own, although you can influence it.
But even then, it's subject to a lot of different things that could happen that are out of control, like the weather, for instance. If there's a sudden heat wave or it becomes cool, or there's a tropical storm or it's raining, you're going to get different properties. You're going to get different triglycerides that form. And so it's kind of interesting to imagine that it's possible you are getting a different piece of chocolate every time.
That is so cool.
Following this fermentation process, the beans are then dried and roasted. And roasted causes a new set of reactions to take place within the beans. It essentially turns them into tiny little chemical factories. So carbohydrates within them, or sugars, essentially are going to break down and caramelize in heat. And these produce a lot of those nutty flavors that you're used to. Next, we get something called a Maillard reaction. And this is when sugars and proteins react with the esters and the acids to produce a variety of flavor molecules. Now, the Maillard reaction is very important and is responsible for a number of different flavors that we're used to. For instance, when you do roasted vegetables, the flavors you get there are from Maillard reactions, even the crust in bread. And so these reactions in chocolate are the ones that are responsible for those nutty and meaty flavors in the chocolate, and they also are there to reduce the bitterness as well. So after this, if you grind up the dried and roasted cocoa beans and you add them to water, you'll actually have the original hot chocolate, which is produced by the Mesoamericans. They called it, I believe, is it chocolatl?
Yeah, chocolatl. And I read about this. It goes back to 1500 BC. Like, we've been drinking chocolate. Chocolates and humans have been around for quite a while. What's interesting, though, is that it didn't actually migrate away from the Mesoamericas into Europe until much later. It was like the 17th century, which is bizarre because we think it's sort of ubiquitous like in nowadays, but it actually wasn't until the 17th century. And even then, it wasn't the chocolate that we have today. It was pretty sort of like thought of as an exotic drink for like next 200 years or so because it was oily and grainy and kind of a heavy thing. And the real key innovation that let it become kind of what we know what it is today is the screw press invention by Van Houten, a Dutch chocolate company in 1828. What this basically allows you to do is you squeeze on this, and as you squeeze on the cocoa butter, you're able to separate the cocoa solids from the fats. You can then, this is really important because then you can dry these things out first off, but it also allows you to change the ratio, right? You're not stuck with the nature's ratio of cocoa solids to butters. You can now separate those and do what you want with them. You can start adding in sugar, and all of a sudden you've got all these different custom mixtures of chocolate, which is why today we have any grade you want of chocolate, from white all the way to pure cocoa, right? And then dark chocolate, milk chocolate in between. This allows you lots of flexibility. The cocoa butter is obviously going to melt in your mouth. It's going to release the cocoa powder and sugar. This is how you make instant hot chocolate, for instance.
Mm-hmm. And then eventually we started adding milk to it. And with the addition of milk fat and various other molecules that are a part of milk, we start to reduce the bitterness and get even more flavors. But one thing that's interesting is that depending on the region of the world, they add milk in different ways or different types of milk. So for instance, in the United States, the fat content of the milk that they add is reduced using enzymes before it's added. In the United Kingdom, they actually add sugar to milk, and then they reduce that to a concentrate, and then they add that to it. But then in other regions of Europe, they still use powdered milk in it, so you get very different flavors, and that's why European chocolate tastes very different than American.
Oh, yeah. And if you haven't tried chocolate from lots of different places, as if you need any other reason to eat more chocolate, but like I would really recommend it because it's crazy. They taste so different. All right, so other than the awesome taste of chocolate, and we're all big fans of it, what other effects does it have, Andrew? I see you've got some cool notes here.
Yeah, I was doing a little bit of digging and found that there's actually a number of psychoactive effects that come from chocolate, which some believe that, or theorize, is one of the reasons why people like it so much. So the first is going to be caffeine. I think a lot of people are very familiar with that. It's a stimulant. The next is going to be theobromine, and this is a stimulant as well as an antioxidant. So if you notice, you can leave chocolate out for a while, and it's not going to go rancid. You're not going to get the mold or anything else that forms in that, and that's because of the sort of antioxidant within the theobromine. However, one thing to note about theobromine, and I believe this has become a lot more well known, is that it's really toxic to dogs. And so what you'll see is around like Easter or Christmas, a lot of families will accidentally, unknowingly feed their dogs chocolate, and it's very poisonous to them. But the effects of it aren't nearly as significant or dangerous on humans.
Yeah, we got a puppy at Christmas, and that was one of the first things I taught them. Dogs can't eat raisins, they can't eat grapes, they can't eat chocolate, they can't eat onions. These things can kill dogs.
Mm-hmm. But one of the more, I guess, interesting psychoactive effects of chocolate is that it's actually an aphrodisiac. And what this essentially means is that when you eat it, it activates the same parts of your brain that are activated when you kiss someone. And they've done a number of studies on this as well, and they've actually found that its aphrodisiac effects, chocolates, are actually much more stronger and longer lasting than if you're just normally kissing someone. So I think they had a number of ads targeting this in the 80s and the 90s, and I think they still do.
That's so interesting to me. In fact, that's actually an interesting segue. I was going to bring this up later, but this whole idea of like that food can act as medicine and the ways that it interacts with our bodies. A friend of mine actually has a podcast. I'm going to throw it out there if people want to check it out. Her name is the name of the podcast is Foodie Pharmacology. And it's from my friend, Dr. Cassandra Quave. She's an ethnobotanist and assistant professor of dermatology and human health at Emory University. I actually met Cassandra in Kuwait City, Kuwait, of all places, last year. And as she was describing what she does, she heads up into the mountains of all sorts of really far off remote places. I think she was in like Kosovo last month or something. Anyway, she finds these really unique plants, and her whole research is identifying how these plants can be used for medicinal purposes and sort of everything on the food health continuum. If you think that's remotely interested, sort of like this chocolate aphrodisiac concept, check out her podcast, Foodie Pharmacology. It's pretty cool. I think you can find it on Apple Podcasts.
Really cool. I'll definitely have to check that one out as well.
Okay, so we're just about wrapped up for today. We do want to say that going from here on out, we'd like to introduce at the very end of each episode a brief, just a minute or two, a question and answer segment. So if you have questions about material science in general, something that we covered, if you want to know more about Andrew or myself or what we do, we'd love to start answering some of those questions. We've been getting some. One great way to do that is by emailing us at materialism.podcast@gmail.com. But we also have pretty good activity on the materials subreddit, and we've actually gotten lots of great content there. People have asked lots of questions. Many of them I think we're going to require more than a minute or two to explain, so we'll probably just convert those to future episodes. But if you have questions, reach out and tell something. Maybe to start with, as an example, I would ask, hey, Andrew, what is material science anyways? Is it going anywhere? What's the future of materials look like?
Right, so this is a pretty common question. I think material science as it is growing quite a bit. It's one of the relatively newer engineering fields. And so, essentially what we're studying is I guess there's two aspects. There's the material science and there's the materials engineering. The science goes into understanding how materials are constructed, looking at them on both the atomic scale and the macro scale, and what sort of properties result from these different structures or the different arrangements of the atoms. But then the engineering side tends to stem from how can we manipulate now these different structures to exhibit the properties that we want for a different application. And so I think a lot of the materials we've made thus far have been rather primitive. And when I say this is if you look at the materials that nature has devised, for instance, a bone, the density of a bone and the structure of the bone actually changes throughout it. It's not uniform. So depending on where it's going to exhibit more force or whether it's going to have a different function or whether it's going to have to support more weight, you're going to see that the bone becomes denser. And in a similar sense, our materials now are starting to get a lot more advanced in that same respect, where we're targeting different functions within a single material. So one part of the material might have a different crystal structure because it's serving a different purpose than another part.
Yeah, just think of like additive manufacturing and 3D printing, which will definitely be a future episode. But think how that allows that to be done. You can have a dense region if you want it, and then you can have a really open cellular region if you want it, and you have a tool that allows you to do that. On the fly. You can change all those parameters as you go manufacturing the final component.
Another sort of instance of that is shape memory alloys, which are starting to become a lot more ubiquitous and more studied, where by introducing either heat or a magnetic field to the material, the crystal structure will actually change and the material will change its shape. And it actually remembers the original shape and can return to that. We'll definitely do an episode on that one as well.
Okay, we hope that you've enjoyed this episode. As always, if you want to learn more, we've got some links for you. If it's about the science of chocolate that's interesting to you, there is a huge body of literature out there. It blew us away. Some of the better publications you could check out, there's a book called Beckett's Industrial Chocolate Manufacture and Use, 5th edition. To my knowledge, this is sort of the gold standard in terms of knowing everything about everything in terms of manufacturing chocolate. So they go into great detail, lots of chapters there. But if you want something shorter, like a specific review article on some topic, there's a great review article on the blooming process, for example, we talked about. It's called Fat Bloom in Chocolate and Compound Coatings. This is by Loneshomt and Hartle, which is really good. As always, Stuff Matters has a little section on it by Mark Miodownik. And then the last thing, if you like to watch YouTube videos, Harvard University actually has a series called The Science of Cooking, and they have a great episode on chocolate that's worth checking out. We'll put links to all these in our show notes.
And as always, if you have any questions or feedback, please send us emails at materialism.podcast@gmail.com. You can also send us any questions for the Q&A segment. In addition, make sure to subscribe to our show on iTunes, Spotify, Google Play, wherever you find your podcast. If you like the show and you want to help us reach even more people, consider leaving us a review. It helps us improve and it exposes us to new people. Finally, check out our Instagram page at materialism.podcast and connect with us to let us know what new material you'd like to hear about next. We'd like to give a shout out to Alphabot for allowing us to use his music within the podcast. You can check him out on Spotify. And as always, a special thanks to Kolobite, who created the intro and outro for the podcast. He makes a ton of really cool synthwave music, which you can check out at kolobite.bandcamp.com. Catch you next time.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world, and are bound only by their imaginations in manipulating those materials.